Hello everybody and welcome to my talk about enabling interactive C++ with Clang. My name is Vassilev and I am a research software engineer with Princeton University. This is a pre-recorded talk, but I'm happy to answer questions at the end of it. Please use the system to ask a question at your convenience and I will make sure it gets answered. The talk is organized in several sections. An introduction where we will discuss about some key insights of interactive C++, such as execution of statements, showing execution results, entity definition, and how to recover from errors. We will use the LLVM-based C++ interpreter Clang to help us on the way. We then will talk about applications of interactive C++. Then we will see how C++ is used in Jupyter Notebooks and how interpreted CUDA C++ can be used for memoization. We will briefly show how to dynamically generate bindings. In section 3, Compiler as a Service, we show possible applications of having a long-lived translation pipeline. We show how to cross the compile time runtime boundaries, how to extend the system via plugins. Section 4, Evolving the Technology Towards Clang, we tried putting that work into context and possibly provide a generic mental model to use when thinking about interpretative C++. We will talk about how to evolve Clang into Clang's mainline, offering a new tool, Clang-Repl. We argue that having a long-lived compilation pipeline which can process C++ incrementally can improve efficiency and offer lifelong optimization opportunities of the application. This talk is about work conducted by myself, but also work of dozens of colleagues and contributors from many domains in science and industry. Any characterizations, mischaracterizations, emphasis, or errors are solely mine and do not necessarily represent the views of other individuals or organizations. This work is partially subsidized by the NSF. Interactive C++ shortens the compile-run cycles, offering a different programming experience along with better productivity in many cases. This particular example is adopted from a YouTube video where the C++ interpreter Clang is used in the context of an OpenGL application. It becomes easier to orient the shape, select the color, and compare to previous settings. In the particular example, we spawn a visualization thread and interactively change the properties of the OpenGL objects. This style of programming allows for better exploration of the problem space. Exploratory programming or rapid application development is an effective way to gain understanding of the requirements for a project, to reduce the complexity of the problem, and to provide an early validation of the system design and implementation. This is especially important for cross-disciplinary domains such as data science. There are several key insights about interactive C++. First, the incremental compilation. This assumes the C++ translation unit is an ever-growing and multiple partial translation units can be added, similar to the namespace partitions. In interactive mode, invalid C++ does not terminate the session. Instead, the invalid code is discarded. Incremental input consists of one or more C++ statements. C++ does not allow expressions on the global scope. An integral part of productivity is printing expression values. Typing printf each time is laborious and does not naturally include object type information. Instead, omitting the semicolon of the last statement of the input tells the interpreter to report the execution result. Name redefinition is an important scripting feature. It also is essential for notebook-based C++, as each cell is somewhat a separate computation. Over the years, there have been several systems which interpreted C++, such as CH, an interpreter and a scripting environment originally designed by Harry Schenk and last released in 2017. Synth, originally developed by Masaharu Goto, last released in 2013, and Clang, the LLVM-based C++ interpreter developed in the field of energy physics to replace Synth in the root software package. It was last released this year. In this talk, we will be using Clang as a reference system for efficient interactive C++. In short, the tool controls the input infrastructure by an interactive prompt or by an interface allowing the incremental processing of input. It sends the input to the underlying Clang library for compilation. Then Clang compiles the input and possibly wrapped into a function and creates an AST. When necessary, the AST is further transformed in order to attach specific behavior. For example, reporting execution results or interpreter-related features. We send back the AST to libclang. Once the high-level representation is ready, it is sent for lowering to a LLVM-specific assembly format, the LLVM IR. The LLVM IR is an input format for the LLVM just-in-time compilation infrastructure. Clang instructs the JIT to run specific functions, translating them into machine code, targeting the underlying device architecture, for example, x86 or NVPTX, which can be then natively run on the target machine. Over the years, an ecosystem around interactive C++ has started to emerge. The Jupyter Notebook technology allows users to create and share documents that contain live code, equations, visualizations, and narrative text. It enables scientists to easily exchange ideas or collaborate by sharing their analysis in a straightforward and reproducible way. Jupyter's official C++ kernel relies on xeus, a C++ implementation of the kernel protocol, and Clang. We can use the visualization system to render rich content, such as images. An advanced example, making use of rich rendering with math-jax and the symbolic engine. In the example, we can see how the corresponding math expressions are drawn into a symbolic form. And interactively, we can ask for help. In the particular example, we type a question mark before a C++ entity, and we will get information about the entity from the relevant page. Of course, the possibilities are more than that. We can have visual widgets organized into controls and other user interface. In this particular example, the slider is attached to a variable and its value can be then used in the rest of the program. Or build something more complicated, like this geo-information system. For more details, you can check out Sylvain's Corlet talk. The Clang CUDA extension brings the workflows to interactive C++ to GPU without losing performance and compatibility with existing software. We can mix C++ and CUDA interactively on the target machine. In theory, this gives us better optimization opportunity. And of course, this works in Jupyter setup. For example, in several laser physics simulation workflows, it can be used for memorization. Here, using the interactive approach, it's useful to relaunch only partial simulation, starting from a given point. For more information, you can visit Simeon's talk. The usual way we teach two languages to talk to each other is by providing bindings. The bindings are usually utilities provided by the library authors to enable crosstalk. Let's take, for example, Python bindings. A common way to use static bindings generators such as Swig, zip, Boost Python, and PyBind11. Some tools rely on limited C++ parsers, which need to be steered by yet another hard-to-use language. Advanced C++ features are hard to support. And more importantly, it is up to your library author to provide such bindings. Alternatively, we could provide bindings on demand, only for the parts of the libraries that we care about. This approach is harder to implement, but it supports features such as template instantiation on demand. Here, an example is cppyy, which provides automatic Python bindings at runtime to C++ through Clang. Another example is the symmetry integration language, SIL, which is a D-based domain-specific language of functional flavor developed and maintained by the Symmetry Investments. Julia has an on-demand C++ interop package called cxxjl. It takes a similar approach to cppyy, but it implements its own incremental compilation logic in its backend. One can conveniently switch back and forth between languages using the Julia REPL environment. Another capability is the Eval-Style Programming. That is, when the interactive system is embedded in a framework, it needs to communicate back and forth execution results. We can use placement new operations to memory address given by the allocator, or we can use an object which can do some lifetime management for us, like the value v in the example. The embedded system can access itself during runtime. In this example, we create an object v of value of type value to store the execution result of the incremented variable v. V boxes the expression result, providing extended lifetime if necessary. This way, we can communicate expression values from the interpreter to compiled code, and that mechanism can be further used to support dynamic scopes, extending the name lookup at runtime, which is used in the root system. Cling is embedded in the root software package. The root package is main tool for storage, research, and visualization of scientific data in the field of high-energy physics. Root is a set of interconnected components that assist scientists from data storage to data processing and visualization. We do not have enough time to look into more details, but you can visit my CppyCon talk on interactive C++ for data science to learn more how Eval-Style Programming is used. We went over some basic and more advanced examples for interactive C++. We saw that interactive and incremental C++ can be very useful addition in some domains. I would like to make several takeaway observations. Cling is not just a REPL, it is an embeddable and extensible execution system for incremental and efficient C++. Cling is used in several high-performance systems to provide reflection and introspection information. Cling can produce efficient code for performance-critical sections where hotspots regions can be annotated with specific optimization levels. We will see more concrete examples in the slides to follow. And Cling allows us to decide how much we want to compile statically and how much we want to defer for the target platform. We saw that the incremental compilation infrastructure can be embedded in frameworks, which can open some interesting capabilities. In a way, we have a compiler as a service which can be used as necessary. The design of Cling, just like Clang, allows it to be used as a library. In the next example, we show how to incorporate libcling in a C++ program. The program can be compiled by your favorite compiler. Cling can be used on demand as a service to compile, modify, describe, or extend C++, but also you can use CUDA. In the next slides, we will see how we can build binaries, including where we can use the compiler as a service to cross the compile time and the runtime boundaries. Let's consider the following example. We have a regular CPP file which creates an instance of the incremental compiler. Then we write a function that at compile time which manages the interpreter object. The function then defines a function queue and compiles it at runtime. Note that we can instruct the system to spend more time optimizing the code if it was a hotspot. Then we take the address of the runtime compiled function from the JIT, cast it to a regular function pointer in the compiled code. Crossing the compiled interpreted boundary relies on the stability of Clang's implementation of the host application binary interface. Over the years, this has been very reliable for both Unix and Windows. Just like Clang, Cling can be extended with plugins. This means that our compiler as a service can be used for domain-specific or application-specific extensions. This example demonstrates an embedded use of Cling's extension for automatic differentiation, CLAD. CLAD transforms Clang's AST to produce derivatives and gradients for mathematical functions. When creating the Cling instance, we can just specify the F plugin option and path to the plugin itself. In the particular case, we request from the compiler as a service to produce a derivative of power of 2 with respect to x. Like in the previous example, we can get the produced function in our compiled code and use it. This approach is particularly useful when power of 2 is a user-defined function. Of course, since gradients or derivatives are often hotspots, we can request a higher optimization level. And here we can also show some candy, where we can print the code that was used to produce the derivative. What's next? We are working towards making some of these features available in the LLVM mainline through a library in Clang and a tool called Clang-Repl. Our main goals are to generalize Cling in a tool that's available in LLVM. We expect to broaden the use of C++ for exploratory programming and also provide an LLVM-centric release cycle. We're working towards consolidating various incremental compilation APIs in Clang, mostly under lib interpreter. We want to further advance the incremental compilation, supporting Clang, and we would like to mention our first results. They were released in LLVM 13. The incremental compilation supporting Clang splits the translation unit into a sequence of partial translation units, or PTUs. Every declaration will be associated with a unique PTU that owns it. Every user input corresponds to a PTU which can be rolled back to a previous state when an error occurs. The first key insight here is that the owning PTU isn't always the active one or the most recent PTU, and it isn't always the PTU of the declaration that comes from. The second key insight is that processing a PTU might extend an earlier PTU, and rolling back a later PTU shouldn't throw away the extension. For example, if the second PTU defines a template and the third PTU requires a template instantiation at float, the template specialization is still part of the second PTU. It eventually should be possible to provide their own slab allocators, which can be thrown away as part of rolling back the PTU if error happens. We saw how partial translation unit works conceptually. Let's create an incremental C++ facility. We create a Clang compiler instance set up for incremental compilation. Then we construct a Clang interpreter, and then we incrementally process code, getting the PTU out and just executing it. We can make slightly more complex example. Here I would like to show an example where a C program can instantiate a C++ template at runtime and call it. I have implemented a small shared library which wraps Clang lib interpreter so that it can be called within C. We have got an example template called call_me in struct B, which just prints the type ID of its parameter. We want to instantiate with a pointer to A. We need to find A and later create a parameter by calling the equivalent of new of A, open close parenthesis. We'll find a class B that contains the template call_me. Then we request the template instantiation at the given parameters. Then we get the function pointer with the newly compiled template at runtime. And we can ask the system to allocate memory on the interpreter side, which is the equivalent of new of A. And finally, we call the function pointer. And you can see here that we also can slightly parameterize the example and pass random types at runtime for instantiation. Now, can we go beyond? We can go beyond C. Let's try to integrate that example into Python. Here I use ctypes to make use of my libinterop.so library, which is a wrapper over the lib interpreter, as we said before. We can parse the same input, template in class B. This input can come by a random header file from a random library. We instantiate a Python class wrapping various functions from lib interpreter to be easier to use it. Then, in our main, we create a Python declarations for A and B. We connect the two callbacks, a handle, which corresponds to our decal of A, and __new__ operation, which can be called when somebody constructs the Python type. We do pretty much the same for B. In addition, we register the call_me function and associate the template wrapper with it, which will manage the instantiation if requested. Then we allocate the Python objects A and B, instructing the compiler as a service to create their C++ analogs. Next, we call b.callme. If explicitly specify the template parameters, the system will create an explicit specialization, or we can select an implicit instantiation. This mechanism is in the core of how we can automatically bind C++ and Python with tools such as cppyy. We saw how to instantiate templates at runtime and how to cross-compile compile time runtime boundaries. Let's try to put that into context and build some intuition. To draw a bigger picture, one can imagine the application development lifecycle. There is development phase, deployment phase, application start phase, and application execution phase. The development phase has the constraints of writing software for an abstract machine and for some abstract user base. The more configurable the software is, the larger the user base it would fit to. That is one of the reasons to introduce software abstractions and indirections such as configuration files. After development, things become very concrete. While we develop the software, configure it, start it, and run it. The static compiler is the classical method to ensure efficient execution by encouraging, if not forcing, people to do as much as possible before deployment. However, the constraints of being generic hinder some of the optimizations. There are more optimization opportunities in the compiler as a service land. For example, after the binary is produced, at the point it is installed and being configured. That is the ahead of compilation time. After it is loaded by the system loader, that is the just-in-time compilation. And while it is being executed, that is the continuous optimization time. This is where we can JIT compile a given graph of functions with O0 to save startup time, and then while executing to recompile with O2 and swap the calls, like the devirtualization and tracing JIT. You can learn more about the Orc V2 capabilities in the Orc V2 tutorial by Lang on the 19th. The static compiler can defer operations to the compiler as a service, but that does not necessarily mean we are sacrificing performance. We just may want to reduce the binary size or avoid template instantiation explosion. But also, the runtime can export information back to the other phases to optimize as necessary. In fact, this is the profile-guided optimization. Another case in interacting with the static compiler is demonstrated here with Clang-Repl. We could register the static archive library and solely use the Orc JIT to materialize the required symbols. In this particular case, we can load LZMA.a and start resolving symbols without relying on the dynamic linker. The cooperation between the static and the runtime compiler can offer some continuous optimization opportunities which can be used to further improve the program efficiency. In summary, I believe we showed interactive C++ is more than just a REPL thing. The compiler as a service provides an opportunity to defer computations until runtime, possibly improving performance and reducing binary sizes. And last but not least, the compiler as a service offers language extensions which can be very useful in some particular domains. Thank you for watching, and I'm happy to answer questions.
All right. Just a reminder to everybody to submit their questions to the Q&A box. And we have one already from Conrad. So the question is Clang only limited to handling C++? It sends code to libclang and gets back IR. What about other languages in the C language family?
Thanks for the question. Currently, our main focus is to support C++, which means that we mostly have coverage there. Over the years, we have had tests and integrations against C, and our runtime, because when Clang starts up, it needs to essentially include some of the header files and some of the information for type printing and whatnot. They need to be in C++, but also we need to provide their analogs for C. And once we provide the analogs for C, we're pretty much supporting most of the languages that the Clang frontend supports. I think the state of C is in a reasonable state. I don't know for Objective-C and Objective-C++, there might be some work needed there.
Yeah, that's an interesting one. I can't speak to the front end part, but the Orc JIT backend has recently acquired the ability to load Objective-C code. So maybe Clang could actually, or Clang-Repl could actually work with this without too much further effort. It's worth trying out.
Yeah, definitely.
I have a question. We don't have any others in the question box yet, but what's the testing strategy for this?
So currently, well, I can split the question into two parts. The first part is what we do in the past, what we have done in the past with Clang. So in Clang, we have test suite, which is pretty stable and reliable, which relies on testing and execution of code on the various systems that we support. And we support a bunch of them. We supported Solaris, and we supported PowerPC and various architectures. But also we can, for the Clang-Repl work, we can use two strategies. The first strategy is to, again, directly test the code the way that we did with Clang, forming reliable and small test cases, which are kind of isolated from the rest of the environment and provide some stable testing facility. But also what we can do is we can rely on the JIT to export some state and then avoid running but compare against the state of the JIT. I think that feature is kind of laborious to implement, and I don't know what is the exact state of that in the LLVM JIT. But I think we should be carefully considering the fact that we rely on the execution tests so that we can test the real environment.
All right. We have another question from Maximilian. How do you handle dangling pointers?
I'm not sure. Dangling pointers in what respect?
We don't have extra context, but I guess
Okay.
perhaps what happens when you reference dangling pointers in this?
It is C and C++. So if you have invalid pointers or something that you are trying to dereference a null pointer, you get a crash. We have a pass which inserts a protection before each dereference so that we can catch a possible problem and not crash the entire process. But I think a better strategy there would be to create an out-of-process JIT execution system and then rely on the fact that if something crashes, then it doesn't crash your process. So I think that is pretty much the long-term strategy there, if that answers the question.
Unfortunately, we're almost out of time, so any other questions we'll have to take offline. But thanks very much, everyone, for coming, and thanks very much, Vassil.
Thanks. Talk to you soon. Bye-bye.
Thanks.